Yeah, it works. It shows here.
Okay, I guess we will get started. Coming back to what we were doing, so we had this term, and then we were trying to volume average all the additive terms.
Can you shrink the screen because the whiteboard is blocking it? Thank you. Move the mic. Or move the mic.
Will that work? No?
No, great. Thank you.
So, as I said, we were at this stage of decomposition. So, essentially, you have an averaged intrinsic phase average, and then the deviation within the REV for that quantity. And I think we had the long discussion here about this is an approximation. It will work if you certain length scale constraints and time scale constraints in some cases are satisfied. So let us see what happens if you take this and say, as I think he showed earlier, one of the consequences of that is that if you take the average of those deviations, they work out to be 0. So without going through that detailed, more accurate, exact estimation, so let's say you take this average of PF. So that means you put that intrinsic phase average plus the deviation, and so you get two of these quantities, and you pull this out. As I said, I'm using a very crude approximation. It's a constant, but as he pointed out, it's just an approximation. Certain length scale constraints have to be met. But let's say all these are met. We think it's kind of constant. We take it out. So phase average of 1 is your porosity. And so the porosity multiplied by intrinsic phase average will give you the phase average here. And so we started with the phase average, and you have another phase average term. So these terms get cancelled, and so you can show that the average of the deviations is equal to 0. So some elementary proof if you don't consider all those Taylor series of expansion and so on. So I will keep it at that level, but if you want to see more details, I think you can see the book, and also I think you should 5-paper series. Okay, so let us see. So we are going to take this, and the basic idea is how to handle this surface integral term, okay? Because here we are getting a nice gradient of the average pressure, so we are getting like a building block of our microscopic equation. But how do we do, what to do with this guy here? So to do this, we basically decompose this, use this decomposition. So as I said, it's a separation of scale. This is what we want, and this is we don't really care about, but we are stuck with that, and we will figure some way out to how to handle that part. So and then we stick it in this surface integral. So and when you put it in surface integral, this is what you get. You have the intrinsic phase average term, and then you have the deviations. And as I said, some approximation, you can So if you follow some constraints, you can pull this out, treat it as a constant, take it out. And this is something that we have to still show. So, so let's say you take I'm going to write down the first averaging theorem for that part. If you recall, it was something like this. Say average of that is equal to gradient of plus you have say 1 over p and then this is F and then no, sorry, this was SFS. And then you have NFS times BF, let's say BS. So this is the first averaging theorem, and I want you to just substitute 1 in place of BF. So in place of BF, you just substitute 1. And so you get something like this. Now bracket of 1, which is phase average of 1, this, as we have seen, this is nothing but porosity. This is like a gradient of porosity. Now right hand side, gradient of 1 is a constant, so that is basically 0. So left hand side is 0. So you have this term is plus this term is equal to 0. So basically this integral which you find here is equal to say volume of REV volume times gradient of porosity, right? So you just substitute this here. So you substitute it here. You take it, substitute it here to get this equation. So this is one of the intermediate equations.
The V is volume or velocity?
This is volume. Capital V is volume. Yeah, generally velocity I will be using small v with the tilde or vector. Okay, so now we are going to use B and C in your A. So this is your B, and that was your B in this A. I guess it's a bit complicated when you. So B and C in A. So yeah, we're still on the pressure term. So you basically have these two terms which come. So this comes from the decomposition. So and then, so you have one term which is negative minus this thing, and then you have this other term which came from the gradient of the pressure field, and so these two terms basically cancel each other, and then we use this D, these two terms here, and we go back to our equation 4, which was this term here. So we stick the pressure, this term, the average of the gradient term here, and come up with all that. So, so this is again another intermediate form here. Now we have to do something about the viscous term. Okay. We would like to develop some kind of averaged equation, averaged variables there. So, okay, so let's just concentrate on this part and treat this as like one entity. So you can apply the averaging theorem. So it's like a tensor. So it's a divergence of the tensor is equal to divergence of the average of that tensor plus this thing. So once again, it is first averaging theorem, but with a tensor here. Now, as I said, these surface integral terms are problematic. This again we will have to do something, because we would like to deal with the averaged quantities, not the gradient of something. So as I said, so here again, in order to handle that, we use this decomposition, average plus deviation, and so this is like gradient of velocity field, so this will become like this, gradients of average plus gradients of deviation. So on using this in this one, you get three terms again. And then here again we have basically used the assumption that this, I think, is a constant. So again you have basically taken this out. So I'm kind of having a lot of constraints there. And then you have this guy, the average of divergence here. So that can be like divergence of average plus this term. Once again, the first averaging theorem. Okay. And so now you can del dot with this term, so that gives you the nice Laplace equation. Now this is something we would like to retain. This is the Laplace of the average velocity. What to do with this guy here? So, as I said, then we apply, we decompose this VF again. No, before we do that, we do something else. Well, we do decompose it here. So you actually substitute your average velocity plus deviation, so you get two integrals, and so the gradient of average velocity is treated like almost like a constant, as I said. It's an approximation, and whatever is left inside, SFS, NFS, ds, that is like gradient of porosity. So you get that term from that, and so you are left with finally is equal to, this is the like a nice Laplace equation term here, and then you have the gradient of porosity term. So it's another one of the Brinkman terms. So you have to have a homogeneous medium, otherwise this term will become important, and the other term here. So we take all this using 6 in our previous equation 5. It's difficult to keep track of 6 and 5. Yeah. So this was our equation 5, and we developed that form for this term, and we substituted there to get our equation 6. Well, this whole equation here. I think if you sit down and work it out, it should be fine. So you can see now we are beginning to get some nice form here. You have the gradient of average pressure, which we want. This is Laplace of the average velocity. Now this is like phase velocity, which is the Darcy velocity. So once again, it is okay. Still, the Darcy form is not coming into picture. We would like to have that. But we do have these two surface integrals here, and then this is one of the Brinkman terms, gradient of porosity. So let us see. So this is the integral, which is the integral of deviations in pressure and then also the deviation in velocity. So here we do a little trick. As I said, this tensor algebra that I taught you earlier, you can write vector times some scalar is equal to vector dotted with identity tensor times that scalar. Okay, just little proof here. A dot I is equal to A. I showed you earlier, you can easily. So once you do this, it becomes much more satisfying reading these kinds of papers. So you can jump from here to here using this little identity, and you can take NFS common outside, and And so this simplification I'm going to put back in our previous equation 7. And so once you put back, you will get this form here. Now I'm assuming porosity to be constant. Can you comment on that part?
The porosity constant. Well, probably it's better to start with porosity constant and do the development, because it's a little bit involved if you take into account the variations of porosity. And for those interested, I may give some references about that particular problem. But that's probably easier to,
yeah, if you just,
for a short course to keep that.
Okay, so we assume the porosity to be constant. So you have a medium which is like a homogeneous medium. Okay, at every point you have the same porosity. There's no gradient in porosity.
So I'm sorry. So how about if for each cell center we have a constant porosity, and that porosity changes throughout the domain? Why do we need to have a homogeneous assumption in order to be able to
No, the assumption of homogeneity actually is important. There are two things. If you keep grad epsilon, you have additional terms in the macroscale equations on one hand, and on the other hand, you have to you will have different closure that will have to take into account the variation of the geometry in the system. This particular aspect is a little bit involved. So, in general, we assume that locally you can discard the variations of the geometry locally. So you can still use those equations for varying porosity and later permeability, provided that those variations are very large characteristic length scales compared to small smaller. Otherwise, there has been papers about the use of macroscale equations with porosity gradients. I even have shown in a paper some years ago. Actually, I've worked on something which is called mushy zones, which are dendritic crystallization forms, which are always varying. And it turns out that the closure problem that Professor Piva introduced is actually very robust. So what I'm saying about the fact that locally I assume this is constant is okay.
Okay, so having that assumption that porosity is constant, so that allows us to basically drop this term. Gradient of porosity is 0, and also temporarily I'm kind of switching from Darcy velocity to intrinsic phase average velocity by using this kind of jump from here to here, epsilon f times intrinsic phase average velocity. So and then that allows me to basically pull out epsilon f out, just keeping the epsilon f constant. I think this is just a note that the volume times the porosity is nothing but the fluid volume. Okay. So we take 9, this equation 9, and you can see there is epsilon f term here, epsilon f term here, and there will be some epsilon f term that will be coming. So we divide, well, here we generate epsilon f term here also from this step. So all this epsilon f can be cancelled by dividing the whole equation by epsilon f, and that will give rise to epsilon f times v. So epsilon f times v. So epsilon is the total volume times the porosity. So that will give you the fluid volume. Okay, so that's what you're going to do there. And so you have the intrinsic phase average of velocity, and then instead of v here you have vf. Okay. Now you can see the nice form of the second Brinkman correction term, which is appearing here. So I think some of you might have worked with Brinkman equation. So generally that term is not very important in a homogeneous medium. Okay?
There has been some discussion on this effective viscosity, whether it should include porosity or not.
Yes.
So it depends on whether you keep porosity variation or not. Things like that. So I will send you through email the reference on papers about keeping porosity in the discussion. So that's probably better.
Because if you use this phase average, you get this effective viscosity. That is rewritten in the...
There is an epsilon, even if it is homogeneous, and there are additional terms if you take a porosity gradient into account.
Yeah, I think there was some discussion about that the effective viscosity term is equal to mu f divided by epsilon, that you can get from here.
I'm sorry, I have another question. So now we are solving for intrinsic velocity, right? So why not to solve for superficial, and then for HR, if we just divide the superficial by the local porosity? Why should we just go through all this and just solve for physical velocity or intrinsic velocity?
You can always do that because you can replace U by the intrinsic by the total divided by epsilon. But it's easy. It's a better thing to start to use for the decomposition the intrinsic average, because it's really related to the phase. So if the fluid the velocity is constant, let's assume we have an Euler fluid flowing in the system, then the deviation is zero, which is a good thing. That's why when you do this kind of decomposition, you always use the intrinsic average, concentrations. If concentration is a constant, then the deviation is zero, and so forth. But you could, I mean, it would be a little bit statistic to do that, but you could use the total average velocity.
Actually, there is a problem with the framing
There's
difference.
a lot of problems.
Framing difference. Actually, coming back to that question, why do we use intrinsic phase average velocity rather than just the phase average velocity? I think I have a couple of sheets at the end. I quickly want to touch over that. If you go back, frame invariance problem. Okay. So frame invariance means, let's say you have two inertial frames. One frame you are stationary, other frame you are moving. Okay, this is stationary, this is moving frame. So let's say fluid velocity within the REV is Vf. And in this case, when your frame of reference is moving with a constant velocity, so you will have velocity within this will be equal to Vf minus V, relative velocity constant. Okay? So let's now take the average, phase average, and see what happens. So when we take the phase average of this moving frame, you have Vf minus V, and it leads to this same development. So and you get epsilon f times velocity, right? Now if you do the same thing with intrinsic phase average, okay, so you have this thing, and Vf minus V, this is a constant velocity, and then intrinsic phase average of 1, this is nothing but, if you look at this thing, 1 f is nothing but 1 over Vf over Vf times Vv, which is nothing but Vf over Vf, which is equal to 1. So the porosity term goes away. Okay, so you get nice relation that even in the moving frame, your the relative velocity will be given by this term. Okay, Whereas in this case, the average relative velocity will be given by this, and then this doesn't make sense. You know, here this average velocity is function of porosity. If you are observing a porous medium in a moving frame, you will get this term. Doesn't make sense. So that's why we use intrinsic phase average for decomposition of velocity. Okay. There's another argument here. If you take the deviation using the intrinsic phase average, so the deviation in the moving frame is equal to the deviation in the original frame. So let's say you are stationary, you study the deviation within the REV. It should be the same whether you are stationary or moving. You will get the same deviation plot. It should be. But if you take, let's say, another deviation, instead of using intrinsic phase average, you are using phase average, you will get this kind of a behavior. Okay? The deviation in the moving frame is deviation plus epsilon. It's a function of porosity. It doesn't make sense. So that the problem of frame invariance is there. So that's why we use the intrinsic phase average for velocity. So this was something, actually, Professor Whittaker, he started with this paper, and then I think it was pointed out by Bill Gray that this is the problem, and then I think he corrected himself. So there's some history behind that.
I have a question.
Yeah.
So, I mean, you wouldn't, two questions. First, you wouldn't have that problem with other variables, right? Like temperature, pressure, stuff like that. You don't.
Yeah, yeah.
The other thing is, I guess as long as you keep track of what these extra terms are in your derivation, you should get to the same answer, no?
You can work on
If you define a different deviation,
Yes,
you just keep track of the
Yeah.
extra terms.
but as I said, it's a little bit
Yeah, right.
more involved, so it's,
Right, sure.
so you want, it's already complicated, so you need to go to easiest way.
Yeah, simplify that thing. Okay, so coming back to this, so this is our kind of one of the intermediate forms, and let's say we throw away this term. This is generally not important in a homogeneous medium. It becomes important at the interface of a porous medium and channel. Okay, then we keep these terms because we want to predict the formation of boundary layer at the interface of free flow channel and the porous medium.
Sorry, can I also ask a question about this? At the interface between free fluid and porous medium, don't you have issues with the averaging volume and stuff like that? So
Most of the length scale constraints don't hold anymore, so you have to develop specific tools to work with that. There are a series of papers about that. Let us say this is still an open problem, because the papers I have in mind, there are some assumptions that have been made that are still questionable. But anyway, the development must take into account different tools. So there are, I can summarize what people have done so far. It's there are many ways to track that. You can do some matching analysis. So if I have a porous medium here, so you have the normal Navier-Stokes equation on one side. If you go far from the divided surface, you can have a Darcy's law or whatever, if you have a finite Reynolds number. And the question is how do you match that? And there are many different techniques. One is just to assume, take for instance Darcy-Neumann, so you have a continuous variation, you have a single equation with continuous variation and different properties. So you have some, for instance, spatially dependent Kx. The question is, how do you build that? But if you're able to do that, then you have something that can be used to develop specific and effective boundary conditions. And so there are many different ways of doing that. The way you match those two macroscale equations, the scales are a little bit different between the two. So there are many things, and there is literature, but this is still an open problem in many cases because of some assumptions which you are forced to do. Please, you won't talk about that today. I mean, so
it will be another series.
You could spend hours on that. And I have a particular point of view, but I know some colleagues have another, so we have very tense discussions about all that. So
Okay, so generally this term is dropped, and so I think we are interested in this part, the basic, this integration, how to handle this integration. And here's some discussion about what are the characteristic values of different terms. So this basically, the whole equation is the order of the order of this term here, and so without going too much into these details, you can read more about that in the book. I just mentioned that you can actually show that this integral here is actually much bigger than this, the Laplace term, which anyway we were kind of planning to throw out. So if you can see, so this is, for example, this term is approximately this term. So you have a deviation in the velocity field, gradient of that. Okay, and then so basically it scales like this. So deviation in the velocity field within the REV, if you look at this term here, let's say you have two particles. So in between the particles you will have, let's say, some kind of a velocity distribution which is like this one. And what I claim here is that this average velocity is basically of the order of f. You can take the magnitude or whatever. So the average velocity here between the particles is of the order of that. Do you agree with this part? Trying to think if you can think of some geometric way, easy geometric way to show that. Generally, let's say you have a porous medium. Let's say you inject some fluid. Let's say its flow rate is Q. Okay. So your Darcy velocity typically is it's approximately Q over A. Well, there is some sign here, but let's say Q over A. So because it's related to specific discharge. Okay, there was one question: why don't we use intrinsic phase average velocity? Why do we use the phase average velocity? it's also related to the history of porous medium. If you look at the experiment that was done by Darcy, he basically could measure the flow rate, and he could measure the cross-section area, and cross-section area, flow rate divided by area, that will give you the specific discharge. Okay, so that is typically treated as your Darcy velocity. Okay. And people like to work with that because of it's convenient. You can do these measurements. Now, of course, you can look into the porous medium and do all the PIV stuff, but it's still very difficult. So if you have this, so this is average velocity that's going through this is Darcy velocity, but the velocity between the particles is not the Darcy velocity. Okay? You can think of like this. Condense all the particles in a solid phase here. And then you have like a channel which is of length, let's say LF. And this is the total length L. So you can see that Q over L, which is the Darcy velocity, we can write that as Q over LF times, say, LF over L. So this is the average velocity in this fluid. So this is your, let's say, VF, and then this is your VF like this, and then this of course is like your. But what I'm trying to say is that this term is actually the intrinsic phase velocity, which will be the average velocity through the pores. Okay. So the velocity between the pores, that's basically the deviation of velocity within the REV. Okay, why? Because you have no slip condition on these particles, so there is zero velocity here, and then there is a maximum velocity at the center. So it's because of the uniqueness of the no slip condition, we have say VF bar that will be of this order. So VF divided by LF, so that will be the gradient of velocity, and then another LF comes from this integral term, which is area divided by volume, so you get this term here, and this is compared with this term. So this is, now as I said, this term, this is like a macroscopic gradient which changes much more slowly, and so then you have length scale corresponding to change in VF, and so all that discussion is there, which is in this book. So bottom line is, these LF squared is much smaller than these two larger length scale, and because of this term is much bigger than this one, and therefore this term is much bigger than this term. So there's another reason why we throw out that term.
LV was the length scale of the REV?
What is that?
Was that the length scale of the REV?
LV?
Yeah.
LV is the characteristic length for, let's say, average velocity variation. LV1 is characteristic length for the gradient of velocity variation. So if you want to be more accurate, it will be something like this. But yeah, typically this you can say LV, big LV of REV.
The REV.
Right? In any case, yeah, these two are much bigger than LF. So we throw out that term, and then you have this term. For homogeneous porous medium, it reduces to this form. Let me do it quickly. So okay, so the problem here is we need to do something about this. We have to find some deviations in pressure. You have to find some deviations in velocity, some way to predict that. And so we develop system of PDEs to solve for pressure deviation and velocity deviation within the REV. And how do we do that? So let's say you have the boundary condition on the SFS, Vf is equal to 0, you decompose it, and then you find an estimation for deviation which is equal to this one. So this is the dominant source term for Vf within this REV. Let's look at the continuity equation. You have the point-wise continuity equation, which is like this. Since this relation holds, the Darcy velocity is equal to intrinsic phase average velocity here like this. You get this term here. This, by the way, is equal to 0 from the macroscopic continuity equation, which we derived earlier. So you get basically this term here. Now this is constant, so this can be thrown out. So the right hand side becomes equal to 0. And so we have this term here. And so we take this and subtract from the term A, which I showed earlier, which was this term here. So you del dot Vf minus del dot average Vf. So that will give you basically this term here, which is the tilde term, the deviation term. So this is one of the PDEs to solve for velocity fluctuations. Similarly, we can get something involving Vf del tilde and Vf tilde. So this is the original Stokes equation we started with, and this is the intermediate form that we reached, equation 10, which I showed earlier. Now you subtract, let us see, you subtract this from this. So look at these terms. So you have gradient of P minus gradient of this thing. So P F minus average, that is the deviation, right? So you get this term. Similarly, rho Fg minus rho Fg goes away. There is no gravity term within the closure formulation here. This minus this, again you get deviation in Vf, which is this term. And nothing minus this term will give you minus of this thing. So this is the spatial deviation momentum equation. So you have one equation here for V tilde, and then another equation for V tilde and P tilde. Okay. So coming together, putting all together, so you have a governing differential equation boundary conditions for the closure problem, because you have to solve for that. So you have one equation here coming from momentum equation, this coming from continuity equation, and then you have these boundary conditions. Now this boundary condition remains the same at the entrance. We don't know the entrance velocity, exit velocity, so we just dump it like this. We don't know this thing. And we have already shown the average of velocity should be equal to 0, so that's another constraint that is put there, which you can easily show, as I said, if you assume Vf to be constant with certain constraints. Okay, so this is the problem. If you want to solve it, we really don't know this thing. That is something that we have to find out. So in order to handle that, I think Whittaker and also Quintard and other people, they developed spatially periodic porous medium. So you have, instead of taking REV, general REV, you have a unit cell. So you have solved the same governing differential equations. You also have the same condition on the interface like this. However, now you don't have the entrance and exit condition, but you impose periodicity boundary condition. Okay, so here you have R is any position vector, so this can be any R vector here plus Li. Li may be L1, L2, L3. So it's like a unit length of the unit cell. So L1 may be like this, L2 may be like this, and so on. So that means that pressure at this point is the same as pressure at this point. So it's assuming periodicity in the pressure distribution and velocity distribution, and also the geometric periodicity. Can you comment on that part, the periodicity condition?
I have a slide on that.
Okay.
Yeah.
So we'll come back to that later. So this is the modified equation. Okay. Any questions about that? Okay. So then what we do is we are basically trying to solve for these deviations, and what people have proposed, starting with Whittaker, I think even before Whittaker, why don't we have a field of a tensor BF and a vector BF, which is something like this one. So deviations in velocity field is B tensor dotted with average velocity. Deviation in pressure is equal to mu times B times this thing. Okay. So in this case, the average velocity is sort of it's kind of taken it away out of the picture. Just deal with in terms of these. So these are something that needs to be found out. Okay. Well, a field of capital B and small b. So we basically take these S1 and S2 and we can substitute it in these equations from here CP1, CP2 and so on till CP5. And you can basically use those tensor manipulation rules to show that you will get this form here. So like pressure is replaced by vector B, the velocity is replaced by tensor B, and then you have these terms here. And then similarly the periodicity conditions are changed. Okay, so now there is this integral term here. What to do with that? So I will show that later, but this was something that was defined to be porosity times the inverse of permeability. I think I will do a little fast forward here. So if you go back to that intermediate equation for momentum, okay, so you have these terms, and then you take these deviations in the form of like this, and you substitute it here. So you get this whole thing, which is multiplied with BF, the average velocity, which is basically coming from here. I think the whole idea was to take this and then assume it to be epsilon time inverse of permeability, and so that you can recover the Darcy's law. So that was the original intent. So that is the definition of that. So we take that definition and put it here. So this is epsilon times inverse of permeability tensor. So you put that, and there is a little transformation here. BF naught is equal to BF plus delta. I'm using delta here, but it's identity matrix in your notes. So delta and identity is the same thing. And so using this, you can easily show that all this will become like this one. These boundary conditions, they transform into this one. It's quite simple, you can show. I think there is one more transformation here, which is this one. So let D is equal to BF dot K, and you do that transformation, and you get with this final form of the closure formulation. So here you have an equation for small d and capital D, and then capital D here, and then this is the boundary condition, and then this is the periodicity condition, and you have a constraint for the average, and that can give you the, basically you can use that to get the permeability tensor from this equation. So you solve this equation in that periodic domain of yours, and you can very nicely get your permeability tensor. So that is one of the strengths of this thing, the closure formulation. So I won't go into the details how this is kind of similar to Stokes' equation. All these details are there, but I think there is some comparison with how does it compare with the experiments. So I think there is a Cozzeni-Karman or Blake-Cozzeni correlation, which is given. As you can see, this is the form. It is equal to some constant here. If you take this, and here different type of porous media, artificial porous media are taken, face-centered cubic, BCC, body-centered cubic, and so on. And for those different cases, it was done way back in 1981, 1982. You could get there is a reasonable comparison between that. I will show some more recent comparisons. Yeah, the same thing. Again, another one, triangular array, square array. So experiment and the theory, the value of this term, which is essentially proportional to the permeability and other terms here. So it matches quite well for these three cases.
So I'm sorry, what is dp?
dp is the particle diameter. Okay.
But it says arrays of cylinders.
Through the array of cylinders. So I would presume it's diameter of the cylinders, I guess. Can you comment?
capillary tube.
Which results are?
dp, this is the Bergelin and then H-sat.
Yes. Well, it depends. There are
I think
I mean, you can define your characteristic length. Best thing if you have a particle system is to use some sort of particle
diameter.
And in chemical engineering, they use specific particle diameter that involves the ratio of specific area, things like that. So you have a particle diameter that depends on the porosity. I don't like that personally, but of course it's a matter of taste if you want.
So I think it comes from bundle theory.
Yes,
the bundle
yes.
tubes theory.
But this does not work very well, for instance, for different forms of more complex media. So this is a completely. Actually, the best thing is to use the square of the permeability as an estimate of some pore throat size. Particle diameter is something, but actually the pressure pressure drop is essentially triggered by small pores or pore throats, and so the characteristic length that should be interesting should be something related to that. So that's an interesting discussion. It depends on. So there are many characteristic lengths available in the literature, and some are connected to ideas of bundles of capillaries, for instance.
Hydraulic diameter.
There are many different things.
So anyway, you can look at the details, original papers, you can find out and see. So it seems that there is a good comparison that is there listed in the textbook here. So coming back to the original equation, as I said, this is the original equation that we had. This was the troublesome term, deviations at the interface, and that was handled by using this vector field BF and the tensor field, capital BF. And so this, if you take this to be epsilon times inverse of permeability, and you substitute it here, you get. You can see it's beginning to look like the final form. You still have this term, as I said, but this is not important in homogeneous medium. So you can do all those things, but anyway, you get this form here, which will have this thing, which is Darcy's law with the Brinkman correction term here, this term. Since this term is generally smaller than this, you can neglect it for homogeneous medium, and then you can recover the nice Darcy's law form here. So it's, I think Darcy's law has been around since 1857 or something, the vector form that came later. But this is like one of the proofs of that. And out of this proof, you get this nice closure formulation, which you can use to find permeability. So I think I will quickly show a little diagram. I think we are a bit late, but I think we actually use that closure formulation to estimate the permeability tensor. So even though it is like comes out of a theoretical proof, but you can use that closure formulation to get a macroscopic property such as permeability, and Professor Quintard will show other methods of using that closure formulation to get the other macroscopic property. So without going too much, I will quickly show in probably in a minute or so. Okay, so anyway, theory of closure equations is there. So what we did here was we actually took like a sintered wick. It's like a small shape like a cigarette, and it's made by taking polymer beads and you fuse them together, and it's kind of a nice material for wicking these kinds of non-water fluid. It's hydrophobic, but it imbibes the alkanes very well. So people wanted us to find out, characterize this, and so we studied the microstructure using SEM and other things. We also did the lab experiment, a simple falling head permeameter to find the permeability, and we compared that with the theoretical and empirical relation for permeability. And so this is the closure formulation which you all know. So we get the Darcy's law. And so we took this closure formulation and we solved it in this. So we take the cross section, you have to do edge analysis and then find out which is solid, which is liquid, and so on. And basically you define a unit cell and solve it, all those things that I showed you earlier. So permeability can be estimated once you get your capital D field from here. So all these different steps were involved. So this is two-dimensional, this is not the full three-dimensional, but it is much faster than full three-dimensional analysis, much cheaper also. So we basically did that, and so we wanted to first see whether it's any good or not, so we compared with the literature result by that paper which is there, and we found that the permeability that is estimated is quite close to that one, and so we were confident with that. And so we went ahead and applied with our real system, and so we did the mesh independent study and also the unit cell size study. We varied the unit cell such that, say, one permeability element value should get some kind of a stable value. So whenever you are doing this upscaling and trying to solve a closure formulation, it's a good idea to change the size of REV also, so that you get some stable value at the end. So cut the long story short, we got a tensor something like this. Now this was a 2D case and you get a tensor like this, but it's mostly, as you can see, almost isotropic material. This is the experiment, falling head permeameter. All this thing is very well known. We did this experiment, we found the value, and so the permeability is like this, and then compares fairly well with the simulation results. These are the physical relations, and these are some of the values from the literature for the permeability. There are tons of these permeability models available, some for particles, some for fibers, some for all kinds of media, as you can see here. So this was the final result. This is simulation using closure formulation. This is the experiment, and Kozenik-Karman here. So you can always beat up the Kozenik-Karman and say, we did well, better than so that's what we did here. But anyway, that is the end of the story, so I don't want to take Dr. Kintart's time too much. And so I will stop here.
Can I use your
Yeah, sure.
that will save commuting the pieces? Is there any
Actually, I have your.
no, but I made a few modifications, so
okay.
yeah. Because I cleaned up, I took so I just yeah. It's in the conferences. Oops.
You can do PowerPoint.
Well, but there will be problem with the equations.
You want to control.
Let me check my computer.
Okay. Yeah, I will take this.
It's not